Orange. Today we will be starting a new topic on pipe flow, that is what we call as pipe network analysis. Well, in the last class itself we did refer to this particular topic while we were discussing say pipe in series or pipe in parallel. Then we were saying that okay, a section of pipe or a stretch of pipe, suppose it is in series or in parallel, but this may be a part of a bigger network. So, of course, not only that issue, but suppose a single pipe, several single pipes can form by joining in the form of a network. Well, so today we will be discussing how this pipe network is existing in different field of say water distribution system, and then how the hydraulics of pipe network is important and how we analyze those things. Well, before going to pipe network, let us see in the last class what we did. Say we were studying practical need of connecting pipes in different pipes of different diameters in series and in parallel. Well, then of course we did discuss how we calculate the head loss in pipe in series, and then of course we were studying how we calculate the pipe loss, the head loss in pipes when they are in parallel. And of course we did refer that parallel does not mean that they should be physically parallel, but the concept of connection is parallel. Well, that we did discuss, and of course again we were discussing that a bypass, say in a main pipe there can be always bypass, and then how by measuring the flow in a small bypass we can have idea or we can know about the discharge in the main pipe. Well, after this now we can move on to the analysis of pipe network. Well, in many water distribution system, the pipelines conveying the water generally branch out and form loops of complex manner. Well, so it is our common experience that whenever we see a pipe distribution system, suppose in city water distribution system, then we see that pipes are forming a network sort of things, and a network is carrying the pipe for carrying discharge to different part. Well, then this complex layout of pipe is called pipe network. Well, now what is the main problem in analyzing this pipe network? The main problem is that okay, when there is a single pipe, say when we were discussing a flow through a single pipe, friction etc. we were discussing, then one point was very much clear to us, that which is the upstream direction, which is the downstream direction. Then that means from which point to which point the water is flowing. Well, but even when the pipe were in series, then also it was very much clear that from which side the flow is flowing, and when the pipes were parallel, then also the direction of flow, there were no confusion about that. We were very much sure about that. But in pipe network analysis, so different network can be there. Well, let me just draw one network of this kind. Say this is one simple network. Say water is coming from this type, this part, and then it is moving this way, and then this way a part is going. Well, from here suppose some water is going out also maybe, then this water is finally going out from this point again, and then water in this pipe is in this direction, in this pipe is in this direction. But suppose if I ask that okay, what will be the direction of flow in this pipe? This can be that water may be moving this way, then it is coming this way, and then it is moving in this direction, or it can be either other way also. Say water is flowing in this direction, then it is moving this way, then it is going this way, and then it is going out from this particular point. Well, so the direction of flow in this particular pipe is not known. This is just a network we are drawing where we have only two loops. Say this is one loop, this is another loop. But there can be network, or there will be network in real situation which will be containing several loops having this sort of common pipe. This pipe is common to this loop as well as that loop. So in this pipe, it is very difficult to say what will be the direction of flow in this particular pipe, and that's the major problem. So determining flow direction in all pipes of the network by simple observation is not possible. And the uncertainty about the flow direction, makes the problem of hydraulic analysis of pipe network more complex. Now, what is hydraulic analysis? That will be coming later, but this makes more complex. Well, the hydraulic analysis of pipe network is achieved on the basis of following condition. Well, hydraulic analysis means, say, when a discharge Q is coming and say we want that Q1 discharge should be flowing in this direction and Q2 should be the final flow, then our interest is to know that how much will be the flow in this particular pipe or in this particular pipe or in this particular pipe or in any of the pipe. This is one region, and then we may be interested to know what will be the head available at this point. Suppose we want a discharge Q at this point, but this discharge will have to be raised to a certain head. Then our interest is to know that how much head will be available at that point. So, that is also one of our interest. Then another interest is that, well, say this diameter, we are not knowing, suppose what should be the diameter. If we fix a pipe of different diameter, then although we need water of say Q1 here, it may happen that this Q1 water is not available there, and as such we will not be getting the required amount of discharge at that point, and that we can achieve by adjusting the diameter of the pipe. Well, so those issues are important, and analyzing those things and designing the pipe network, all those are coming as a part of hydraulic analysis of pipe network. Well, and this is achieved. This hydraulic analysis is achieved on the basis of following conditions. Okay, what are those conditions? The basis of hydraulic analysis, the first condition is that the continuity equation must be satisfied. Now, where continuity equation must be satisfied at every node, that we can write. Means, say this is a junction point. Node means, okay, let me call this as a junction, at a junction point. Now, so this is a junction, and suppose a amount of Q1 is coming in this direction, Q2 is going in this direction, and then Q3 is going in this direction. Now, what this continuity condition is, that Q1, that is which is coming into this particular point, this is a node, suppose Q1 is coming into this. So, Q1 and what is going out, this must be equal, Q2 plus Q3. That means, the flow coming into a junction, say flow coming in is equal to flow going out. And that is true not only for a point which is just a inner point, or which is, suppose each pipe are a part of the network. Say if I draw a network like this, again that same network, simple network, then suppose at this point if water is coming here, going there, and then it is also, suppose from this side it is coming, then we can say that Q1, Q2, Q3, in that case we can say that at this point Q1 plus Q3 both are coming in is equal to Q2. Well, then again suppose, well, this is the discharge which is coming in Q, and this is the discharge which is going out, say Q out. Now, at this point say discharge through this pipe which is coming in, and this pipe it is coming in, and going out is this point. Well, so this is suppose Q4 and Q5, let me give this name as Q out. So, what will be the continuity condition? We will say at this point that Q4 plus Q5 must be equal to Q out. Okay. Similarly, here also if there is a discharge like this, say Q6 is going, or suppose let me give a name, say Q6, okay, this be Q6, then say this is Q7, then what we can write the continuity condition. If I write for this particular point, then what we can write, say Q7, which is coming in minus Q3 which is going out minus Q4 which is going out and Q6 is also going out, minus Q6 is equal to 0. Well, or say we can say Q7 is equal to Q3 plus Q7 is equal to Q3 plus Q4 plus Q6. So, this is what is continuity condition and this must be satisfied. That is the most important point, and based on this continuity condition, first we assign a logical value of discharge in each of the pipe during our pipe network analysis, and after that of course we need to do iteration based on other condition. Now, let us see what are the other conditions that need to be satisfied. Well, the other condition that is the basis of hydraulic analysis based on already one condition we have discussed, then second condition that flow in each pipe satisfy the head loss equation. Flow in each pipe satisfy the head loss equation, that is the Darcy-Weisbach equation, and of course we normally use the Hazen-Williams equation here, not the Hazen-Poiseuille equation, Hazen-Williams equation, and this is not just we can derive from here directly as say head loss is say proportional to Q to the power n, that way we can derive. Well, we know Darcy-Weisbach equation, that condition what we discussed earlier regarding Darcy-Weisbach equation, for what condition it is applied, and those condition we assume that this is satisfied. Now, considering that, what we have, that is head loss HL is equal to say FL V square by twice G D, that is the Darcy-Weisbach equation. Okay. Now, starting from this, what we can write, that HL is equal to say FL, F is the friction factor as we know, L is the length of the pipe, and then V is the velocity of flow. Of course, we talk about average velocity when we talk say velocity of flow in a pipe. At the central line, the pipe flow velocity will be more, but we are talking about the average velocity in the pipe. And then D is the diameter of the pipe, G is the acceleration due to gravity. But this V square can be written as say Q square by area. Area is nothing but pi by 4 D square. So, it is whole square that we can write. So, what we can write this value, say V square we can write Q square by A square. Area is nothing but pi by 4 D square whole square. So, area square. So, this is what we are writing for V, and then twice G and D. Okay, let us use the same symbol for diameter as we are writing here capital. Let me write here also capital value, capital, because diameter we are writing here as capital D, fine, at least in this analysis. So, now this expression we can write as say FL Q square, FL Q square, well another D was there here, this is coming from the area and this D is already there. So, this is there, FL Q square, then it is twice G, then we can write pi by 4 square, we can simplify this, but let it be like that, we are not worried for that expression, then D square whole square, it is D to the power 4, then another D, so it is D to the power 5. Now, for a given diameter of pipe, if the diameter of the pipe is given, then if the friction factor of the pipe is known, and if length of the pipe is known or given, then for this particular pipe, that means for a given pipe, what we can write, that HL, what we can write, that HL is equal to, this part we can consider as a constant, this part we can consider as a constant, and we can write K, K Q square. Of course, the Hazen-Williams gave this expression not as HL is equal to KQ square, Hazen-Williams gave this as HL is equal to KQ to the power n. And then of course, he said that for turbulent flow, fully turbulent flow, or say for when the flow is moving towards turbulent, then this n value can be taken as equal to 2. And of course, this in lower side the n varies from say 1.8 around to 2. So, that way this n can be very well for practical purpose we can assume this as 2, because if we consider the head loss to be on little higher side, so far distribution is concerned we will be in safer side. So, we consider that HL is equal to KQ square, n is equal to 2 if we consider, then it become HL equal to KQ square. Okay. And this expression is generally used. So, this is the second condition that we need to satisfy or that we need to know. We have discussed two conditions till now. One is the continuity condition must be satisfied, second is the head loss must be satisfy head loss equation of this Darcy-Weisbach or this Hazen-Williams equation is valid. Well, then the third condition, and third condition is the most important condition for analyzing pipe network. Well, what it states that algebraic sum of head loss around any closed circuit must be 0. Around any closed circuit must be 0. Well, say a flow is occurring in a circuit. Okay. So, this is the circuit. Now, flow is coming from this side and say it is moving this way, then it is coming up this way and then it is coming this way and then it is meeting at this point. Well, then what will happen? Well, let me draw another point. This is just one loop I am drawing. Again, if I take this example, there also we can have loop like this. And there can be, suppose I can draw here also one more pipe. Say these are pipe like that. And I can put another pipe. So, there will be two loop like that. And from this side, the water may be moving out also. Well, like that similarly, here say one loop and then this is one loop, and this is another loop. Okay. This way the water is going out, Q in, Q out, and there may be another Q out at this point. Well, now this loop, suppose water is flowing from this side, it is going like this and it is coming like this and it is coming like this. Now, in this closed circuit, this is a closed circuit. In this closed circuit, if we calculate the head loss, say from here to here we are getting a head loss. From here to here we can see that water is coming, there will be some head loss in this line, then again from here to here there will be head loss. Now, if I try to calculate the head loss around this closed loop, then if we sum up the head loss here, ACL1 suppose, then ACL2, then ACL3, if I sum up all the head loss, then we will be getting that from here to here we have some head loss. Now, when we are seeing from the beginning, say at this point we have some head available. Now, if I just go and turn around the loop and reach here, then head available here will become say H minus HL1 plus HL2 plus say HL3. But we know one point, that in any water distribution system, at a particular section or at a particular point, there cannot be two different head. At a particular point, energy level should be same. So, now what will be the condition? Say from this point we are starting with a available head of H, and then when we are returning to this point we are finding that head available is this much. That means that head loss, what we are considering to be as loss, this must be equal to 0. Head loss around a closed loop must be equal to 0. Otherwise, the condition that head at this point is H initial head, this should be equal to that, cannot be satisfied. If it is to be satisfied, this will have to be equal to 0. So, that is the third condition, and this is the very basic condition which we apply and we try to solve the pipe network problem. In fact, as I said initially, we keep some discharge based on the continuity condition, and then we see that whether the head loss around each of the closed loop, not only in one closed loop, there will be several closed loop in the entire pipe network. So, whether head loss in each of the closed loops are 0 or not. If not, if it is yes, then it is fine, but if not, then we need to apply correction. Well, so let us see step by step what this step may be, that method of solving pipe network problem. Different scientists have attempted solving this problem in different way. So this complicated problem of pipe network is generally solved by trial and error procedure. Whatever may be the procedure, generally it include the trial and error procedure. Well, and different methods have been developed for solution of this particular problem, and Hardy-Cross, we need to remember this name, Hardy-Cross in 1934 developed the method of successive approximation. They named this method as method of successive approximation. That means it is basically it is a iteration. Initially we assume some value, that is the approximate value we are assuming. Then we are solving it and we are trying it to see whether this condition is satisfied, head loss equal to 0 around a closed loop, and if it is not, then we are getting another approximate value. But how to get this approximate value, that procedure we need to discuss, but we will be getting another approximate value. Then with that approximate value, with this corrected revised value, we will again check whether head loss around the closed loop is 0 or not. So that is what the procedure is. This method is quite convenient and is widely used even now. Well, of course, some other works are there. Say water distribution system was studied by, say, McIlroy in 1951. Well, so he studied this McIlroy, he studied in, say, in 1951 by electrical analogy method. Well, we know that various problem in our hydraulic engineering, particularly say when we talk about flow through porous media, head loss in that case, that we study by electrical analogy method, that is pipe, I mean this is not pipe, what we say that flow net. Flow net, of course, you will have to get the concept of flow net in fluid mechanics, or even in soil mechanics we get this concept, and then there also we apply, say, electrical analogy method, and here he applied electrical analogy method and he solved this pipe network problem. Then method of equalizing storage was presented by M.B. Mifferson in 1960. And Martin and Peters introduced Newton-Raphson method. Newton-Raphson method is a known method in mathematics, and that was applied for solution of this pipe network problem. Then William in 1973 developed a technique for quick convergence of this cross method and balancing heat, cross method of balancing heat. So this method was there, and this method he tried to have quick convergence in this method. And we in 1988 we tried to develop a computer solution of pipe network capable of handling any number of loop. So whatever may be the number of loop, we just need to give the loop sketch, and then from that, by using a computer program we develop, then it can solve the solution for the pipe network by Hardy-Cross method. And then different numerical methods have been used for solution of the pipe network problem, and then nowadays commercially lot of softwares are also available, commercial software are available. I do not want to name this software, but various softwares are available for solution of the pipe network problem. Well, because here perhaps in this class we will not be going into the quite detail of this pipe network analysis, because when we are talking about pipe network, maybe that we are talking about, say, simple pipe connecting and then forming a network, but there will be a valve, there will be different other component in between the pipe network. Well, so incorporating all these things, if we try to solve, then of course it become more complicated. And now softwares are available, or simply we can apply our concept and we can develop a computer program for solving this sort of pipe network problem also. Well, then let us see what is Hardy-Cross method, which is widely used and which is very popular till today. Let us start with steps in Hardy-Cross method. Understanding each and every steps in Hardy-Cross method is of course important. Well, first step is that most reasonable discharge in each pipe is assumed satisfying continuity condition. I am repeating this point from the beginning, that first assume discharge is made or considered based on the satisfaction of the continuity condition. Well, then next step, that is the head loss in each pipe is computed by Hazen-Williams equation, that is K is equal to, head loss HL is equal to K Q to the power n, and this n can be considered as 2 for practical purpose. Next step is the summation of head loss around a closed loop is calculated. Now, at this point we should be careful. Say if we calculate the summation of head loss around a closed loop, and if we just keep on adding the head loss, it will never be equal to 0. Say for example, as I did draw here first the loop here, say HL1, definitely from here to here there is a length, definitely from here to here there is a width. Well, I mean there are diameter is there, length is there, f value is there, so we will be getting some head loss. And if we go by the k q square relation, then say k value will be there for this, it will never be negative, k value for a pipe will never be negative. As you can see, if we go to our previous slide, that k value is FL twice z pi by 4 d square, out of this nothing is negative. So, this k value, which is this one basically, and so this will never be negative. So, k value will be there. So, k q square, if we calculate the k q square, then it will never be negative. So, if we try to add this value, then here also some positive value, here also some positive value, here also some positive value. If we try to add these things, then it will never be equal to 0. So, summation of head loss that way cannot become 0. So, we will have to apply a concept here, that head loss when it is in the suppose clockwise direction, when flow is in the clockwise direction, then we will consider the head loss to be positive. And when the flow in a pipe is in the anti-clockwise direction, then we will be considering that head loss is negative, because we are talking about head loss around a closed conduit. Now, if we are calculating the head loss from here to here, suppose a pipe is, water is flowing from here to here, we can calculate head loss. But if the water is flowing from here to here, and if we are calculating head loss in this direction, that means say from here to here head loss will be what? This head loss is more, this head is more at this point, and this head is less. So, from here to here if we calculate head loss, definitely there is no loss, rather we are gaining the head, and that is why the head loss in case of the flow where the flow is in anti-clockwise direction, then we can consider it as negative. Well, of course, this is our point at whether we consider clockwise or anti-clockwise, but generally clockwise direction flow head loss is considered positive, then anti-clockwise flow in a particular pipe we consider the head loss that we calculate as negative, and that we will have to consider, otherwise our problem will not be solved. So, this point is important. Well, say head loss around a closed loop is calculated by considering clockwise flow as positive and anti-clockwise flow as negative, or we can say head loss for a clockwise flow as positive, head loss for an anti-clockwise flow as negative. Fine. In order to satisfy summation of head loss equal to 0, the flow is adjusted by applying a correction delta Q. So, once we get the head loss in each and every pipe of each and every loop, then we try to check what is the summation of head loss in each of the loop, and definitely with our first assumption this will never become 0, then we need to apply some correction. So, if our initial discharge we are considering is Q0, then we will have to apply correction delta Q. So, final revised flow will be Q minus delta Q. So, that delta Q is very critical, and then we need to find out some way of calculating this delta Q. Well, so let us see how we can calculate the value of delta Q. Fine. So, calculation of delta Q. Well, in a pipe, well, let me always keep this diagram here. So, suppose we are talking about this loop, and say in a pipe, flow in this pipe, say okay, let us first write for one pipe, say it is Q0. Well, so let the trial discharge. So, first trial we are considering the discharge is Q0. Here it will be again Q0, I mean different value of Q0 we can trial. So, let the trial discharge be represented by, we can write like this, be represented by Q0. Let the correction is equal to delta Q, and then what we can that revise or say correct, revised or correct flow. Initially we are considering this to be correct, I mean after applying the correction. So, revised or correct flow, we can have that Q is equal to Q. So, what we can have that Q is equal to, this revised flow is equal to Q0 minus delta Q. Well, Q0 minus delta Q. Well, now what is head loss? Say head loss, say for the corrected flow, what we can have, head loss is equal to K Q to the power n. Let us keep it in the form of Q to the power n first. Later on we can make it 2. So, K Q to the power n. N is we are keeping in general term. Well, this can be written as, this is nothing but this is equal to say K Q0 minus delta Q to the power n. Now, this if we expand this in a binomial series, then what we can write this, say HL, let us expand this in the form that is equal to K, then we can write that Q0 to the power n minus say n Q0 to the power n minus 1, then delta Q, and then of course we can keep on writing terms here. In the second term, in the next term, what it will be coming, this will be n minus 2 and this will be delta Q square. Then after that it will be delta Q cube. So, that way this term will be, this power of this particular term will be increasing in our steps if we keep on writing here. Now, we know that delta Q, that correction is very small as compared to the assumed flow, because assumed flow will have to assumed on the basis of our understanding of the diameter or the K value of a pipe. K value represent everything. I mean, say loss in terms of say this coefficient represent length, then friction factor, diameter, combining everything, it gives a K value which represent the head loss is proportional to Q and with this proportionality constant K. So, that takes care of everything. So, as we are assuming to some extent logically the value, we can consider that Q is very small. Of course, that way, because we are not getting explicitly, so it will require some trial and error procedure. Okay, first let us consider that as delta Q is very small, as delta Q is very small. So, when a small quantity is there, suppose 0.5 or something very small, then this small quantity to the power some power, say to the power square or say cube, this will become further smaller, as 0.5 to the power square or 0.5 square become say 0.25, it is smaller than this cube, it will be further smaller. So, if it is a smaller value for delta Q, then we have the delta Q is very small, as delta Q is very small. So, higher power of delta Q will be much smaller, will be much smaller. Therefore, neglecting the terms considering delta Q neglecting the term containing say delta Q square, delta Q cube, or whatever it may be, we are not writing those part. I mean, this second term, next term will be containing say delta Q square, then after that delta Q cube, like that. So, because first is delta Q. So, we are neglecting all those terms which contain delta square, Q square, delta Q cube. So, neglecting the terms containing this, what we can write, that now we can write say SL is equal to K Q0 to the power n minus n Q0 to the power n minus 1 and delta Q. Okay. So, here we are neglecting the other part. Now, for a loop, what we have, that summation of head loss, we are talking about a loop only. For a loop, summation of head loss should be equal to 0. So, summation of head loss is equal to 0. This implies that summation of k Q0 to the power n minus say summation of k n Q0 to the power n minus 1 into delta Q is equal to 0. In place of HL, we are putting this term and we are getting these things. Now, in this summation expression, what is the delta Q? That is the correction what we will be applying. That correction what we will be applying. That correction is basically same for all the members of that particular loop. But here we are not talking about all the members of the entire network. What we are talking about is the members of a particular loop, and in that particular loop, the delta Q, the correction what we will be applying is same for all the pipes in that particular loop. So, delta Q is constant for the members of a loop. So, delta Q, when we are talking summation, this Q0 and this value will be different, K value will be different, Q0 for each pipe will be different, but this delta Q is same. So, this delta Q we can keep out from this summation side, common, rather we can take common and we can write like this. So, this implies say summation of K Q0 to the power n minus delta Q into summation of K n Q0 to the power n minus 1 is equal to 0, and this implies that delta Q is equal to say summation of K Q0 to the power n divided by summation of K n Q0 to the power n minus 1. Fine. Now, putting n equal to 2, we have got the expression. So, putting say n equal to 2, what we can write, delta Q is equal to summation of K Q0 square and then summation of K n will become 1 now, it is summation of K, n will become 2. So, we can write summation of twice K Q0, twice K Q0, n minus 1 will become 1. So, this power is 1. Well, so this is how we need to calculate delta Q. Now, while calculating delta Q, there is one important point, that when we will be summing up this value, so we know that our head loss should become 0, delta Q should become, actually summation of head loss should become 0, means the correction should become smaller and it should become 0 finally. But this delta Q square, if you take the Q value of each and every pipe and we are squaring it, whether we consider the direction to be negative or positive, I mean if it is squared up, then it will become say all positive. So, that we should not do. So, we will have to specify some very specific point about that. The numerator, this value should be summed up considering, well, numerically value is considered the k q0 square, that value is fine, but it should be considered positive or negative based on the direction of flow, But this value we should add up straight away, whether it is positive or negative. I mean, everything we should take the absolute value. Well, so taking this absolute value of this part and considering the positive and negative sign for clockwise and anti-clockwise in the numerator, but denominator is absolute value, we need to add up for this twice k q0. Then this value will become bigger, finally this ratio will become smaller, and that way we will be getting the correction delta q. Well, now after doing this correction or after calculating this delta q, what we should do, the checking after applying the correction. What sort of checking we need to do? In case of members, first point, in case of members common to two loops, correction for each loop need to be applied to these members. Well, say this, well, I am not using the diagram I have drawn earlier. Here again I am drawing a fresh diagram. Say this is a member which is common to this loop. Suppose in this loop we are getting a correction, and again this is a loop where we will be getting some, that means let me name this, say A, B, C and D. So in the loop, okay, in the loop say A, B, D, in the loop A, B, D, say correction is delta q1. So here say the charge is q. Now let me write q1, q2 and say q3. Let the discharge, first assume the charge is q1, q2 and q3. Okay. Now after all our calculation, summation of k, q, and k value is say k1, this is k2, this is k3. So we can calculate head loss in each of the pipe, k q1 square, k q2 square, k q3 square, and then we are assuming say flow in this direction is like that, flow in this direction is like that, and flow in this direction is this one. So by this loop, say while calculating the correction, what we will be doing, as the flow here is clockwise, we are considering k q1 square is positive. Here also it is clockwise in this direction. So our loop is this one, so it is clockwise. So k2 q2 square is also positive. But this, our loop is in this direction, it is rotating like that, but the flow is in the opposite direction. So this we will be considering k3 q3 square will be considered negative. And of course, when we are calculating twice kq, we are just taking absolute value and we are summing up, because we want to calculate the correction in head loss. Well, correction required to making the head loss 0, that is why we are considering it like that. Now doing all those calculation using this expression, we will be getting a value of delta q for this particular loop. So after applying correction, what will be the value here? If delta q value is positive, that we should know. If delta q value after calculation, if we are getting the delta q to be positive, means our correction is positive, means correction we are considering, wow, here we are considering that correction in a way that if this is the revised flow, then original flow minus the correction. So when correction value itself we are getting positive, that means if the flow is clockwise, this is positive. So in clockwise flow, correction, if the value we are getting positive, this value will have to be deducted to get the revised value. But if our correction value is getting negative, then from clockwise flow it should be added. For clockwise flow it should be added. That means q0 minus, then minus delta q. If the value itself is negative, that will have to add. So that are some, these are some critical point, and that we need to consider. So here let me show, suppose our delta q value is positive. Well, we are getting some delta q value. So what will be the revised flow in this pipe? This is positive means, and this is yet clockwise. So correction is, or corrected value will be q1 minus delta q. Well, so this I am writing delta q dash say. let me write this as delta q dash. Dash means this is the correction for this particular loop. And then what will be this q2 value? This q2 value will be say q2, this is also clockwise flow is, so q2 minus delta q dash. And what about this q3? Here flow is anti-clockwise, so here what is that? q3 plus delta q dash, q3 plus delta q dash. That means in a sense, in a easier way, in another way also you can say that if delta q correction is positive, we are applying say minus delta q. That means we are considering the delta q is flowing in the opposite direction. So when it is facing delta q in the opposite direction, flow will become negative. Flow will become q2 minus delta q. Here it is q1 minus delta q, but here it is in the direction of the flow. Correction is we are giving in the opposite direction because it is minus delta q. We are starting in the starting itself we have considered. So it is q3 plus delta q. Well, then say this value is this one. Now for this common member, what is happening? Say for this loop also, for the loop say B, D, C, our correction is say delta q double dash. Okay. Now this correction when we are applying say in this loop also, suppose it is q4, this is q5, then this will become, if the delta q is positive, this will become q4 minus q5, and this will become q5, sorry, not q5, q4 minus delta q double dash, this is q5 minus delta q. Well, this flow is in this direction, then it will be plus, because this is loop is like that and this is in the anti-clockwise direction. So it will be q5 plus delta q double dash. And then what about this one? In this pipe, original value is q2. Now correction from this particular loop is q2 minus delta q dash, but again for correction from this particular loop is there, that correction is in fact this is in the direction of opposite, it is clockwise direction is like that, so flow is in the opposite direction. So this will be again plus delta q dash, delta q double dash. So this flow finally will be q2 minus delta q dash plus say delta q double dash. Like that we need to apply the correction from both the loop to this particular pipe to have the corrected value. But this procedure is followed to get the corrected value, and then the condition a summation of ACL equal to 0 should be checked with the revised flow after applying corrections. So once we apply the correction to each and every loop, there may be several loop again connecting to this one, there may be several loop like that. So applying the correction to these loops, we need to again recheck whether we are now having the condition that summation of ACL equal to 0 or not. Well, once we get this value summation of ACL equal to 0, then we should stop, that okay, we have got the correct value. If not, then we need to again repeat the procedure starting from calculation of a new delta q0 and then solving it for a new and then deducting or reading based on whether it is positive or negative, we can get the solution. So this procedure is followed in Hardy-Cross method, and this procedure need to be repeated until desired accuracy is obtained. So here we do not say that we will be going up to the 0 value, we will not be going up to the 0 value of delta q. But say if our discharge is of the order say 50 qmac, or I mean this order maybe 5 qmac, 6 qmac, that is order, then when our, if in that case suppose delta q value is coming in decimal say 0.2, say if it is 5 or 5.2, it does not make much difference, that correction we may not apply. So based on our total flow or say approximate flow what it should be or order of flow that we are getting, based on that we should stop once our correction become smaller, well, so significantly smaller to influence the revised value. Once our delta q is very small, even if we apply the correction, the revised value will not change, and with that suppose revised value will not change significantly, then again if we repeat, we will be getting same order of correction and revised value will not change, it will be fluctuating between that. So we should not come to 0, but we should come to a desired accuracy level. That is what the procedure of solving the pipe network by Hardy-Cross method. Well, now let us see that in quickly, let us just see quickly taking a problem and to see that how we can solve this problem. I am taking a solved problem from the book, but just to explain how this problem is solved, and let us see, say the problem is again this typical loop what we are talking about already. This loop is there. Say a discharge of 100 is coming, whether it is QMAC or whatever it is, that we are not interested right at this moment. Say discharge of 100 is coming, and this loop name is A, B, then say C and D. Okay. And then from this point, say from the point B, there is a outflow of 20. Okay. Then from D, there is a outflow of 50. Well, then from again the entire continuity also must be satisfied. Say if 100 QMAC is coming, 20 is going from this side, 50 is going from this side. If nothing is given and just say something is going out from this side also, that point, then it must be equal to 30, because the total going out and total coming into the loop must be same first. Then let us apply our just understanding or general experience, and let us see how we can divide the discharge into different pipe. Okay. Well, before that, let us keep some k value. Say k here is equal to 5. Well, this is 2. K here is equal to 5. Then k, this value is equal to 1. Then k of AC is equal to 4, k of CD is equal to again 1. Okay. Now let us assume the first approximation. Say as this k value is smaller, that means head loss k q to the power n, or rather when k value is smaller, we can assume that we can consider that roughness is less, or say total resistance offered is less, or head loss will be less in this direction. So for a smaller k value, we can always consider the higher discharge. So let us first assume that 100 will be divided like this. Here it will be going 70 and here it is coming 30. Well, then from this point, say 20 is going out. So remaining is, now we need to check continuity at each point. Here the continuity is satisfied, 100 coming in, 70 and 30 going out means 100 going out. Now here 70 is coming in. So from 70 we need to see that 20 must be going out, because it is already given in the problem. So remaining is 50. Now we need to just divide this 50. So this k value is very large, 5, as compared to this k value. So what we can assume that this k value is less, means let this be 35 out of 50, then this is say 15. Well, then 35 is coming in this direction and 30 is coming from this direction. So this value must be say this value must be, let us calculate, 35 is coming from this direction, 35 is coming from this direction. Well, 30 is again going out from this point, that we need to check. 30 is going out from this point. So here in this direction it must be 35. Then only say 30 plus 35 must be equal to 30, which is going out this point, and 35 which is going out from this node. So that way now it is satisfying all the conditions. Let us verify if our assumptions are correct. Say 15 is coming from this point, 35 is going. So 15 plus 35 is equal to 50, and finally 50 is going out from this point. Well, so that way first approximation of the discharge we have put now. We will be able to show you one step of calculation, let us see, and then we can of course do practice with the other steps. Well, we can solve this in the form of a table, say. Well, first let us consider the loop A, B, C, loop A, B, C. Okay. So in the loop ABC, what are the member? Say AB, then BC, and then CA. Okay. Now our interest is to find KQ square value, and of course we will be calculating say twice KQ, this value. Let me write KQ square here and twice KQ here. Well, then if we put the value of K and Q square, I am just directly writing this value. This value, okay, one step, say the here AB K is equal to 2 and 70 square, this value is equal to 9800. Well, the next value will be 1225, means in this, these are positive because clockwise, but this value which is in the opposite direction will become negative. So what this negative value is? It is say minus, we can write 4 into 30 square. So this value will become minus 3600. Now if we sum up this value, then it becomes the summation of KQ square, this is becoming 7425. Then what about twice KQ? This twice KQ is becoming 280 for first loop, then this is 70. Here we are not considering positive negative sign, everything is absolute value, 240. So this value is becoming 590. So summation of twice KQ is becoming 590. Fine. Then if we calculate the delta Q, so this delta Q is becoming equal to say 7425 divided by 590, this is equal to 13. So this delta Q is the correction for this particular loop. Well, then loop means ABC. Then if we consider loop say BDC, BDC means BDC. So in this BDC loop, again we can calculate say KQ square and twice KQ, and the member we can write down here, say member we can write say member BD then DC and CB, BD from here to here, DC and CD. Okay. Now KQ square here, it will be 1125, then this will be negative because it is in the opposite direction, so it is minus 1225. I am not showing the calculation. This value will also be minus 1225 because here also 35 in the anti-clockwise direction, here also 35 in the anti-clockwise direction. K value is 1, K value is 1 here. So for both the pipe it will be the same. Then we can calculate what is summation of KQ square. Summation of KQ square is becoming minus 1325, and whether twice KQ, this value will be 150, then this is 70 and it is 70 again. So you can check the calculation later, and this is 290 twice KQ. So this value summation of twice KQ. So here the correction say delta Q is equal to, we are having say minus 1325 divided by 290, and this is equal to, we are getting minus 5. Well, so this correction we are getting minus 5, and this correction we are getting plus 5. We can write this as 1 and this as 2. Now if we apply this correction, how this flow will change? Well, now this delta Q1 and delta Q, we are getting the value. Well, now let me see, or let us see how we can apply this correction to this our earlier loop. So here in this, and here we are putting the delta Q is equal to 13. So plus 13 means that we will have to deduct from the clockwise flow, and minus 5 means that we will have to add to the clockwise flow, and just the reverse things we will have to do here. So delta Q is equal to 13. So if we just recall what was our original assumed value, it was 70. So this value will be 70 minus 13. So this value will become now 57. And then if we see this particular pipe, here our first assumed value was 35. Well, So, first assumed value it was 35. So, now it will be, this is also clockwise. So, from 35 we need to deduct 13. So, right now we are not deducting this, we know that because there is, this is a member common to this one as well as this one. So, what we will do, say here it should be 35 minus 13, but we are not deducting that right now, we are keeping it here. And then this pipe, as we can see, this pipe, as we can see here, if we apply the correction, then it is anti-clockwise, this flow is anti-clockwise. So, this 13 we will have to add here. If we add this 13, then earlier this flow was 30. So, now if we add 13, then it will become say 43. Well, then similarly in this loop it is minus 5, this correction is minus 5. So, earlier flow in this it is clockwise, so correction is minus means we will have to add to the clockwise flow. So, earlier this flow was, first assumed flow was 15. So, now this flow will be 15 plus 5, that will be 20. And then here this earlier assumed flow was say 35. So, now this new flow will be 35 here, but the flow is anti-clockwise. So, it is anti-clockwise and correction is negative. So, from anti-clockwise we will have to deduct. So, it was earlier we had this earlier flow was this one 35. So, now it will be 30 here after correction. So, it will be 30. And what about this? This flow earlier was our 35. So, here this 35 and then our this flow is say in the opposite direction. So, we need to this flow is in anti-clockwise direction, our flow is this direction, clockwise is this one, this is anti-clockwise direction. So, from anti-clockwise flow the negative flow should be deducted, positive flow should be added to anti-clockwise flow. So, it is negative flow, so that we will have to deduct from here. So, earlier it was 35, that should be again minus 5. So, what we will be getting, say 35, then again minus 5 will be coming. So, it will be total will be minus 5. So, this will be say 30 minus 13, finally this will become say 17, this will become 17. Well, so like that we are getting the different flow distributed in this entire network. And now we can of course verify whether our condition is satisfied or not, because this is very important. We can check, say 100 is coming, 57 is going out, 43 is going out, 43 plus 57 again it is 100. So, at this point continuity condition is satisfied. At this condition, say 57 is coming in, 17 is going out, 20 is going out and 20 is going out. So, 20 plus 20 40 plus 17 57. So, total 57 is going out from this and this, 57 is coming in. Here also if we check, our continuity condition will be satisfied. Then again if we check here, 20 is coming in, 30 is coming in, 50 is going out, our continuity condition is satisfied. But this head loss condition again may not be satisfied. So, how to check? We again need to check, because K value are known, again K value are not changing, these are remaining same. Of course, if we consider in this pipe flow problem, if we consider FL V square by twice Z or FL Q square, those formula if we consider, and if F value we consider to be varying with the Reynolds number, then of course our K value can keep on changing. We can use a variable K value or this roughness value. Then of course every time we need to calculate Reynolds number and indirectly we need to check that value. But here of course for simple situation we are considering K to be constant, and that way we can again calculate the same, we can repeat the procedure and we can see whether our summation of head loss is satisfied. Rather what we are calculating, we should calculate the delta Q in both the loop. And when we will be getting delta Q in both the loop to be very small as compared to the order of the discharge that is flowing in different pipe, then we can say that our flow what we are getting is correct flow. And that repetition, of course, we do not have sufficient time to complete the entire repetition, because this will require 3-4 repetition to make the delta Q very small. Well, but I hope that we tried to explain the procedure, and I hope that this procedure we have explained. And so if you try to do the same procedure, if you try for the for calculating the discharge value in the next few step again, and then if you check it after 2-3 trial, I hope you will be getting the correct result. So with this, we are concluding our class on this pipe network analysis. In the next class, we will be going for some more interesting topic of pipe flow, that is, which are very much important in water power sector, like water hammer, and those things we will be discussing in our next class. Thank you very much.